Many of us have experiences seeing a spark or hearing a crackle that we take off our synthetic shirts or nylon sweaters. Particularly in dry weather, sometimes we feel like the sensation of an electric shock while opening the door of our car or by holding the iron bar of a bus. After sliding from our seat, the reason of rubbing the insulating surface. Another common example of electric discharge in lightning that we see in the sky during the thunderstorm. We know that the glass rod is rubbed with a piece of silk. The rod acquires the property of attracting light objects like bits of paper, straws, pith balls, dry leaves, or even just dust particles towards it. The glass rod is said to be electrified or charged. Similarly, a plastic comb gets electrified on passing through a dry hair. The metallic bodies of cars and trucks are also charged because of friction between them and the air rushing past them. This charge being taken can produce even a spark. Such a spark can be dangerous in the case of petrol tanker. That is why petrol tankers often you have a metal chain dragging from the ground. The charge produced leaks to the ground through this chain. Nowadays, the tires of cars and trucks are made by adding of carbon compound to the rubber. This facilitates the charge to build up on the body of the vehicle to leak to the ground. We learn from the above the electric charge can produce due to the friction between two insulating bodies which are rubbed against each other. The charges on insulating bodies can move on their own. This is why they are called as static charges. The branch of physics that we deals with the study of charges at rest, or you can say a static charge. The force between the static charges, fields and potential due to these charges is called electrostatic or static electricity or frictional electricity. Historically, the phenomenon was discovered around 600 BC by Greek philosopher Thales of Miletus. The name electricity was taken from the Greek word electron. Note is that the most important and clearly experiments of electrostatic works best on the dry day because excessive moisture provides pathway of the charge to the leak of charge object. The first question that arrives in our mind is that what is an electric charge? Electric charge is the characteristics that accompanies fundamental particles which they exist. According to William Gilbert, charge is something possessed by the material objects that makes it possible for them to exert electrical force and respond to the electrical force. The three most common elementary particles are electrons, protons and neutrons having masses 9.10940 into 10 to the power minus 31 kg. Mass of proton is 1.67262 into 10 to the power minus 27 kg. And mass of neutron is estimated to be same as the mass of proton, which is 1.67493 into 10 to the power minus 27 kg. Because of their masses, these particles attract one another by gravitational forces. Thus, an electron attracts another electron at a distance of 1 centimeter with a gravitational force of 5.5 into 10 to the power minus 67 Newton. However, an electron repels another electron at a distance of 1 centimeter with a force of 2.13 into 10 to the power minus 24 Newton. This force is called electrical force. We observe that the electrical force is very large compared to that of gravitational force. The electron must have some additional property which is responsible for the electrical force between them. This additional property of electron which gives rise to the electrical force between two electrons is called electric charge. Just masses are responsible for gravitational force. Charges are responsible for the electrical force. Two protons placed at the distance of 1 centimeter also repel each other with the same force of 2.3 into 10 to the power minus 24 Newton. It shows that the protons also have the charge which the magnitude must be equal to the charge on electron. Two neutrons placed at a distance of 1 centimeter attract each other with a force of 1.9 to 10 to the power minus 60 Newton, which is a gravitational force due to their masses. However, the electrical force between two neutrons is zero. Therefore, neutrons have no charge through they have mass. Two kinds of charges. Let us look at some simple facts which we established from the years of efforts and careful experiments. The glass rod rubbed with a piece of silk is brought close to the suspended glass rod rubbed with the silk repels each other. The latter is shown in the figure in other page. The two pieces of silk of cloth in which the glass rod were rubbed also repel each other. However, each glass rod attracts the silk piece with which it was rubbed. Two ebonite or amber rods rubbed with cat's fur repel each other as shown. Each ebonite rod attracts the cat's fur through which it was rubbed. An ebonite rod rubbed with cat's fur attracts a glass rod rubbed with a piece of silk as shown. However, the charged glass rod repels cat's fur. When a glass rod rubbed with a piece of silk is made to touch with small pith balls suspended by the silk nylon threads and balls repel each other. Similarly, when the ebonite amber rod is rubbed with cat's fur is made to touch two small pith balls suspended by silk or nylon threads, the balls repel each other as shown. However, a pith ball touched with charged glass rod attract another pith ball touched with the charged ebonite rod. A careful analysis of these facts observed leads us to following conclusions. The bodies like glass rods, ebonite, amber rods, silk, fur, etc. acquire electric charge on rubbing. The pith balls or the polystyrene balls acquire electric charge by actual contact with the charged body. The charge developed on the glass rod rubbed with the silk is different from the charge developed on the ebonite rod rubbed with fur. This is because a charged glass rod repels other charged glass rod but attracts a charged ebonite rod. Hence, there are two kinds of charges. When the glass rod is rubbed with silk, the rod acquires the one kind of charge and silk acquires second kind of charge. This is true for any pair of objects that is rubbed to be electrified. When an electrified glass rod is brought in contact with the silk piece with which it was rubbed, they no longer attract each other. They also do not attract other light objects as they did on being electrified. It means the charge acquired on rubbing are lost when the two oppositely charged bodies are brought in contact with each other. It leads us to the conclusion that the charges acquired by the objects on rubbing against each other must be equal to the opposite. And that's why neutralize each other's effect. Dufay was the first to show two kinds of charges, and American scientist Benjamin Franklin named the two kinds of charges as positive and negative. By convention, charge acquired by glass rod or cat's fur is called positive, and the charge acquired by ebonite or amber or silk cloth is negative. Hence, there are two kinds of charges. The property which differentiate two charges is called polarity of charge. If a body possesses an electric charge, it is said to be charged on in electrified. When it has no charge, it is said to be neutral. Further note that the only rubbed area of non-conducting body gets charged and the charge does not move to the other parts of the body. The charge is static on the rubbed portion only. What is the role of electrostatic play in Xerox copying machine? This is a frequently asked question which answers you almost know is that a Xerox copying machine is one of the many industrial applications of the forces of attraction and repulsion between charged bodies. Particles of black powder called toner slick or tiny carrier bed of the machine on account of electrostatic forces. The negatively charged toner particles are attracted from carrier bed to the rotating drum, where a positively charged image or document being copied has formed. The charged sheet of paper then attracts the toner particles from the drum to itself. They are then heat fused in place to produce the photocopy. When your friend chooses a wintergreen lifesaver in a dark room, you see a faint flash of blue light from his mouth. How? The display of light is often called sparking. It occurs due to electric discharge of electrostatic charges produced in chewing the wintergreen lifesaver. Conductors, insulators, and dielectrics. Most of the substances in nature are divided into two categories, namely conductors, insulators, and the substances which can be easily used to conduct electricity from one end to another is called a conductor. Silver is one of the best conductors. Other examples of conductors are copper, iron, aluminium, mercury, coal, etc. Earth is a good conductor also. Human body is also a good conductor of electricity. The liquid conductors include salt, solution, acids, alkalis, etc. In metallic conductors, there are a very large number of free electrons which act as carriers of charge. In fact, the mental and the outer valence electrons part away from the atoms are the free to roam about the body of the metal, but they cannot leave the metal under normal circumstances. The free electrons from the kind of the electron matters, but they cannot gas. They collide with another and also with the ions and move randomly in different directions in an external electric field. The free electrons drift against the direction of the field. The residual atoms made up of nuclei and bond electrons remain held in the fixed positions. They constitute the bond charges in the conductor as they cannot move. In electrolytic conductors, the charge carriers are both the positive and the negative ions. The insulator are the materials which cannot conduct electricity. They are poor conductor of electricity. Common examples of insulators are glass, rubber, plastic, ebonite, mica, wax, paper, wood, etc. etc. They are called insulators because they prevent charge from going to places where it does not desire. Such substances possess almost no free electrons. In fact, in an insulator, each electron is attached or bound to the particular atom is not free to move. In the body of the insulator, as each the electron says its parent nucleus or within an atom or molecule and cannot move far away from it. Therefore, an insulator does not possess free movable charges, hence it fails to conduct electricity. Insulators are also called as dielectrics. Obviously, dielectrics cannot conduct electricity. However, when an external electric field is applied, induced charges appears on the surface of the dielectric. Hence, we may define dielectrics as insulating materials which transmit electric effects without conducting. When some charge is transferred to a conductor, it gets distributed readily over the entire surface of the conductor. In contrast, if some charge is put on an insulator, it stays at the same place. A nylon or plastic comb gets electrified on combing dry hair or on rubbing, but a metallic rod does not get electrified on rubbing. This is because the charges on metal leak through our body to the ground, as both are good conductor of electricity. When a charged body is brought near the contact with the earth, all the excessive charge on the body disappears by causing a momentary current to pass through the ground through the body. This process of sharpening the charges in the earth is called as grounding or earthing. Earthing or the grounding near the main supplies of the building is done by burying a neutral earth or metal wire deep into the earth, and there is connected to a thick metal plate. The electric wiring in our house has three wires: live, neutral, and earth. The first two carry electric current from the power station, and the third is connected to the buried metal plate. Metal bodies of the appliances like TV, refrigerators, electric iron, etc., are connected to the earth wire. If a live wire were touched to the metallic body, the charge flows to the earth without damaging the appliances and without causing injury to us. Gold leaf electroscope, which is also known as a GLE experiment. A gold leaf electroscope, or GLE, is an instrument which helps in detecting the presence of electric charge and its polarity. The instrument can be used for measuring potential difference. The essential part of the gold leaf electroscope are shown, with two extremely thin gold foils attached to the lower end of the metal rod are fitted in the glass jar through the insulating stopper S of the cork or rubber, etc. D is a metal disc at the free end of the metal rod. The sensitivity of the instrument is increased by passing two tin foils on the inner side of the glass jar opposite to the gold leaves. As the gold leaves are extremely thin conducting foils which have low mass per unit area and are flexible, therefore they respond very quickly to even a small electrostatic force. Thin aluminum foils can also serve the same purpose. When the charge rod is touched with the metal disc D, the same charge is transferred to the gold leaves through the metal rod. The leaves repel each other and diverge. By measuring the divergence of leaves, the amount of charge in the body can be estimated. The diagram looks very simple of a gold leaf, which is figure 1a.3. This is the particular diagram of a GLE gold leaf electroscope. Origin of electric charge in electrostatics. It is known that all matter is made up of atoms and or molecules. The basic unit being an atom. We also know that every atom consists of a central core called atomic nucleus, which is negatively charged electrons revolve in circular orbits. Every atom is electrically neutral and containing as many as electrons as the number of protons in the nucleus. Thus, even though normally the materials are electrically neutral, they do not contain charges, but their charges are exactly balanced. The vast amount of charge in an object is usually hidden as the object contains equal amount of positively charged and negatively charged. With such quantity or balance of a charge, the object is said to be electrically neutral. It contains no net charge. If the positive and negative charges are not in balance and there is net charge, thus an object is charged if it has a charge of imbalance or some net charge. Hence, to electrify a charged and neutral body, when we need to add or to remove one kind of charge, there we can say that the body is charged. We always refer to the excess charge of deficit charge. What happens is that most of the electrons are less tightly bound in the atom. These are the charges which are transferred from one body to another. When we rub two insulating surfaces against each other, we provide energy to overcome friction between them. This energy is used in removing electrons from one substance and transferring them to the other. The transfer takes place from one material in which electrons are held less tightly will lower work proportional to the material in which the electrons are held more tightly with higher work function. Electrons are transferred from material whose work function is lower and the material whose work function is higher. Consequently, the material which loses electrons acquires a positive charge and the material which gains electrons acquires an equal negative charge. For example, if you rub a glass rod with a silk, electrons are transferred from glass rod to the silk. The glass rod becomes positively charged and the silk acquires an equal negative charge. Thus, the charging by rubbing due to the actual transfer of electrons. The cause of charging is actual transfer to the electrons from one material to another. The insulating material, which lowers the work function, can lose its electrons and become positively charged and vice versa. Further, as an electron has a mass, however small it may be, therefore there does occur some change in mass or changing. The positively charged body has lost some electrons and hence its mass reduces slightly. On the other hand, a negatively charged body has gained some electrons and hence its mass increases slightly. Note is that in rubbing two insulating bodies, the number of electrons are transferred is a very small fraction to the total number of electrons in the material bodies. Hence, the charge acquired by the friction is very small, which is 10 to the power minus 6 coulomb of the total positive and negative charge content of the bodies. Further, as only one less tightly bound electrons in a material body cannot be transferred from it to another by rubbing. Only under unstable suitable conditions we have to stick to certain pairs of materials to observe charging on rubbing the bodies. We have listed the pairs of objects which get charged on rubbing against each other. They may have divided into two classes, one acquiring positive charge and another acquiring negative charge on rubbing. Objects acquiring positive charge or negative charge on running. Positive charge comes with something like glass rod, fur or woolen cloth, woolen coat, woolen carpet, nylon or acetate dry hair. Negative charge comes from things like silk cloth, ebonite amber, or rubber rod, and plastic sheet, rubber shoes, cloth, comb, wood, other thing. Obviously, two charged objects in the same column repel each other, and the two charged objects of two different columns attract each other. Further, divided substances can be arranged in a series called tri-bioelectric series, while any two of the substances in series are rubbed together. The ones occurring earlier in the series acquires both positive charge and other occurring later in series requires negative charge. Some of the substances in triboelectric series are fur, fennel, wood, glass, papers, cotton, silk, wood, metals, rubber, Orion, polythene, Teflon, ebonite, and there are many much examples for that. The glass acquires a positive charge when rubbed with silk, and it requires a negatively charged when rubbed with fur. We know that the body charging by induction. We know that the body can charge by putting it in contact with other body either directly or by means of the conductor. For example, when a charged ebonite rod is contact with the pith ball or connected to a copper wire, it transfers some of its negative charge to the pith ball. This is charging by conduction. When a charged body A is brought near an uncharged metallic body B, then some charge of the opposite sign appears on the near face of the body B, which is equal to the charge of same sign appears to the near face of the body. The total charge on the body B is 0. In this process, body A does not lose any charge or it does not in direct contact with body B. The phenomenon of charging the body B is called as charging by induction. The phenomenon of charging an uncharged conducting body by bringing a charged body near it without making a direct contact between the two bodies is called as charging by induction. There is the steps involved in charging a metallic sphere by induction as shown in the figure. To begin with, metallic sphere on an insulating stand is uncharged. When a positively charged glass rod is brought near the uncharged metallic sphere, free electrons of the sphere are attracted and start piling up to the end near this end therefore becomes negatively charged and farther end of the sphere becomes positively charged. To the same extent, due to deficit of electrons as the sphere on the whole remains neutral. The redistribution of charge is almost instantaneous and stops as soon as the net force on the free electrons in the metallic sphere becomes zero. When the sphere is grounded and connected to the earth by conducting wire, electrons flow from the ground to the sphere and neutralize the positive charge on the farther end of the sphere. The negative charge at the end of the sphere remains bound there due to its attractive force of glass rod. When the sphere is disconnected and the ground and the negatively charged continues to held on the here end. When the glass rod is removed, the negatively charged spreads uniformly over the sphere. Similarly, steps are involved when a negatively charged rod is used for charging the sphere positively by the induction. Let us now understand how we charge two spheres by induction. As in the given shown figure down, shows two metal spheres A and B supported on the insulating stands, held in the contact with each other. Let a positively charged glass rod to be brought near the sphere. Free electrons in both the spheres are attracted towards the rods, and therefore the left surface and the right surface has excess of negative charge and right surface of right sphere has an excessive of positive charge. Note point to be noted is that the electrons in the sphere have not accumulated on left surface of the sphere. This is because a negatively charged starts building up the left. Further electrons are repelled by these and equilibrium is reached almost instantly under the action of force of attraction of the rod and the force of repulsion due to the accumulated negative charges. Shows the equilibrium situation. Further, the accumulated charge would remain on the surface as shown till the glass rod is held near the sphere. If the rod were removed, the charges would return to the original neutral state in the absence of any outside force. Separate the spheres A and B by a small distance, with the glass rod is still held near the sphere A. The two spheres carry opposite charge as shown. They attract each other. Remove the glass rod. The status of charge on the spheres is shown. When the spheres are now separated widely, the charges on them gets uniformly distributed as shown. This is how two metal spheres get oppositely charged by induction. Note is that in this process of electric conduction, the positively charged glass rod does not lose any charge. This is contrary to charging by conduction and charging actual contact where charged glass rod loses some charge. The quantization of electric charge is the property by virtue of which the charge of a body is internally multiple of a basic unit of charge of an electron proton represented by E. Thus, the charge of a body is always given by Q is equal to N. When N is an integer positive or negative, the basic unit of charge is called a charge of proton. Carries by convection current on electron is taken to be negative. Therefore, charge on electron is written as minus E and the charge of proton is written as plus E. The value of basic unit of charge is elementary charge is E is equal to 1.6 into 10 to the power minus 19 coulomb. It is one of the most important constants of nature. If a body contains N1 electrons and N2 protons, the total number of charge on the body is Q is equal to N2 E plus N1 minus E is equal to N2 minus N1. The common is E. As N1 and N2 are the integers, the difference must not be an integer. Therefore, charge on the body is always an integral multiple of E, and there can be increase or decrease also steps of E. Thus, a charged body or a charged particle can possess charge equally plus 1 electron, plus 2 and plus 3 electron. And also on the positively charged values of charge are 1.6 into 10 power minus 19. For q is equal to 1 positive 1 electron. For equal to q is equal to 2 electron is 3.2 into 10 power minus 19 coulomb. For q is equal to 3, it is 4.8 into 10 power minus 19 coulomb. And so on, the values of charge lying in between these values are not possible. The cause of quantization is that only integer multiple of the electrons can be transferred from one object body to another. For example, when an electron is transferred from charge acquired by the two bodies, while q is equal to 1 electron and 1.6 into 10 to the power minus 19 coulomb. Similarly, when n electrons are transferred, the charges acquired by the two bodies will be q is equal to any where 1.6 into 10 to the power minus 19 coulomb. Recent discoveries have shown that the neutron protons made up of the quarks. The quantization of the charge was first suggested to be the experimental laws of electrolysis discovered by the Faraday. It was actually demonstrated experimentally by Millikan in 1912. Thus, quantization of the charge is experimentally verified in all domains of the nature, like charge, energy, and angular momentum are also quantized. Quantization of a charge is meaningful at the microscopic level, where the charges involved are of the order of few tens or hundreds. They can be counted. Such charges appear in discrete lumps, and quantization of charge cannot be improved. However, the microscopic level we deal with charge is the microcoulomb. A charge of magnitude 1 microcoulomb contains electrons whose number is q is equal to n by e. 1 into 10 to the power minus 6 coulomb by 1.6 into 10 to the power minus 19 coulomb, which is equals to 10 to the power 30, which is very large. At this scale, the effect of the charge can increase at the distance only the units of E is not visible. The grainy nature of the charge is lost and it appears to be continuous. The situations can be compared with geometrical concepts of the points and the lines. A dotted line viewed from the distance appears continuous to us, but it is not continuous in reality. As many points very close to one another normally give an expression of the continuous line. Many small charges taken together appear as to be continuous charge distribution. Hence, at the microscopic level, quantization of the charge has no practical consequences. It can be ignored. Here is one of the questions: that is the charge of 5.8 into 10 to the power minus 18 coulomb possible? Solutions: we can see that q is equal to n, where n is equal to q by e. So after solving 5.8 into 10 to the power minus 18 by 1.6 into 10 to the power minus 19, which is equal to 36.25. As n is not an integer, the value of charge is not possible. Additivity of charge. Additivity of a charge is a property by virtue of which total charge of a system is obtained simply by adding algebraically all the charges present anywhere on the system. It means charges are scalars like the mass of a body and are added by simple laws of mathematics. If a system contains n charges, like q1 plus q2 plus q3 and dot 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 to qn, then the total charge of the system is q is equal to q1 plus q2 plus q3 and multiple more. Charge has magnitude only but no direction. Similar to the mass, however, mass of the body is always positive, but charge can be either positive or negative. Therefore, proper signs have to be used while adding the charges in a system. For example, if a system contains a charge of plus q, minus 2q, and minus plus 3q and 5q, then the total charge of a system is equal to plus q minus 2q, which is around to be, after solving that, we're going to have plus 7q. Conservation of charge. Conservation of charge is a property by virtue of which total charge of an isolated system always remains constant or conserved. Within an isolated system consisting of many charged bodies, charges may not distributed due to interactions among the bodies, and the total charge of a system shall remain the same. For example, when the rub two insulating bodies, that one gains in charge and other body loses for same amount of charge, thus it is possible for energy to destroy the net charge carrier by any isolated system, so charge carrying particles may be created or destroyed in the process. For example, note that the equations given the forces between two charges in vacuum only. More about the Coulomb's law. Coulomb's law is a universal force which binds the electrons to the nucleus to form the atoms is calculated from this law. The sum law applies to van der Waals forces which unite the atoms to form molecules. These three states of matter with solid, liquid and gases are also explained on the basis of this law. Coulomb's law has been verified over distance ranging from nuclear dimensions 10 to the power minus 15 meter to the microscopic distance 10 to the power 18 meter. Further, the law is applicable only to the point charges. There is limitations of Coulomb's law. Coulomb's law of electrostatic force between two charges corresponds to Newton's law of gravitation. Force between two masses F is equal to G m1 m2 by r squared, where G is the universal gravitational constant 6.67 into 10 to the power minus 11 Newton meter square per kg square. This value is much smaller as compared to the value of electrostatic force constant K is equal to 9 to 10 to the power minus 9 Newton meter square for Coulomb square. That is why electrostatic forces are far more stronger than the gravitational forces. This is evident from the fact of the charged glass rod attracts a piece of paper against the gravitational pull on Earth on the paper. Further, whereas electrostatic force may be attractive or repulsive depending on the sign of charges, gravitational force is always attractive. Importance of Coulomb's law of electric force in vector form. The Coulomb's force between two-point charges as stated by Coulomb's law supports Newton's third law of motion. The Coulomb force is an central force as it acts along a line joining the two-point charges. The Coulomb force is a conservative force as the work done in taking a charge from one point to another in an electric field is another charge is independent of the path followed. Units of the charge. The SI unit of charge is Coulomb. We can define unit charge from equation 3. Suppose Q is equal to Q1, Q2 is equal to Q, R is equal to 1 M and F is equal to 9 to 10 to the power 9 Newton. From the above calculations, after solving this we get 1 Coulomb. Hence, the SI unit of SI in 1 Coulomb is that much charge in which placed in the vacuum at the distance of 1 meter from equal and similar charge would repel its force from 9 to 10 to the power 9 Newton. The CGS unit of charge is 1 electrostatic unit of charge or stat coulomb. It is also called 1 Franklin in honor of the American scientist Franklin for his contributions to the study of electrostatics. As the charge of electron is 4.8 into 10 to the power minus 10 stat coulomb, therefore the 1 Coulomb is equal to, after solving that, we'll get 3 into 10 to the power 9 stat coulomb. Yet another unit of charge is electromagnetic of charge, unit of charge EMU, whereas 1 EMU is charge of 3 into 10 to the power 10 ESU of charge stat coulomb, which is equal to 10 coulomb. Dielectric constant or relative electrical permittivity. When the charges are situated in a medium other than the free space between them is given by 1 by 4 pi epsilon into Q1 Q2 by r square, where epsilon is the absolute electrical permittivity of intervening medium. The force between two charges held the same distance apart in the vacuum is 1 by 4 pi epsilon naught into Q1 Q2 by r square, which is also known epsilon by epsilon naught is equal to epsilon r, or which is called K. When E is the relative electrical permittivity of the medium, it is also called dielectric constant of the medium and is denoted by K. Dielectric constant of a medium is the ratio of absolute electrical permittivity of the medium to the absolute electrical permittivity of the free space. Also, dielectric constants of a medium may be defined as the ratio of force of interaction between 2 point charges separated by a certain distance in air vacuum, or the force of attraction repulsion, and same 2-point charges held at the same distance apart in the medium. The value K depends upon the nature of the medium. For example, for vacuum K is equal to 1, for air K is equal to 1.006, for hydrogen K is equal to 1.00026, for glass K is equal to 3 to 4, for mica K is equal to 3 to 6, and for water it is K is equal to 81, and so on. Thus the force between two given charges is held at the distance apart in the water in only one unit of the force between the air and the vacuum. The forces between the multiple charges, principle of superposition. The mutual electrical force between two charges is given by Coulomb's law. However, when we have to calculate the force on the charge due to several stationary charges, we use the principle of superposition in the addition to Coulomb's law. According to superposition principle, total force or any charge due to the number of other charges is addressed as the vector sum of all forces and that of charge due to other charges take at the time. The forces due to individual charges are if unaffected by the presence and absence of the other charges. Suppose a point charges q1, q2 and q3 are situated at the points with the vector positions of r1, r2 and r3 respectively with respect to the origin O of the rectangular coordinate system xyz. In general, total force on the test of the position is due to the discrete charge can be written as this. This is the force on q0 due to q1, even though the charges are present. Similarly, force on q0 due to q2 where other charges are present is given by this particular formula, which is at the end we can see F is equal to Q by epsilon naught epsilon and Qi by R naught by Ri. The direction of net force of F naught on charge Q naught due to the discrete changes can be determined using polynomial law of vectors. Continuous charge distribution. As the charge can exist only the integral multiple of the basic charge, therefore charge distribution is always discrete. On account of the automaticity of charge, however, this impractical work in terms of discrete charges always. For example, on the surface of the charged conductor, we cannot specify the charge distribution in terms of allocations of a microscopic charge constitute. However, we can consider a small area in element delta S on the surface of the conductor. This area element is very small on the microscopic scale but big enough to include a very large number of electrons. In delta Q is the most amount of charge in the element. We define surface charge density at the area element by sigma is equal to delta Q by delta S. We can repeat the process at the different points on the surface of the conductor and thus arrive at a continuous function sigma with the surface density. At the macroscopic level, charge distribution is discontinuous as there are discrete changes separated by intervening space where there is no charge. Therefore, sigma represents macroscopic surface charge density, which is smoothed out average of the microscopic charge density over an area delta S, which is small macroscopically but large macroscopically. On this same basis, the charge is distributed along a line, straight or curved we define. Linear charge density is given by delta Q by delta L, where delta L is a small line element of the wire on the microscopic scale that includes a large number of microscopic charge constituents, and delta Q is the charge contained at the line element. The units of delta in centimeter. The volume charge density defined as a similar planar as P is equal to delta Q by delta V, where delta Q is the charge included in the microscopically and small amount of element delta V that includes large number of microscopic charge constituents. The units of P are C by M, centimeter by meter cube. Note that the motion of continuous charge distribution is similar to the continuous mass distribution in mechanics. For example, when we talk about the density of a liquid, we are referring to microscopic density, treating it as a continuous fluid and ignoring the discrete molecular constitution. Force due to continuous distribution of charges. The force due to continuous charge distribution can be obtained in almost the same way for the system of discrete charges. Suppose a continuous charge distribution in space has a volume charge density P with respect to the charge P in the function Ri. Let it may be vary from point divide the distribution into small volume elements of size delta V. Therefore, charge in this volume element delta Q is equal to V delta V. Consider any general point inside the charge distribution with a position vector or P vector is equal to R naught vector. Using Coulomb's law, the force due to change element dq is the smallest charge Q naught is P, where R is the distance between the charge element at the point P and the R vector is a unit vector directed element to the point P as is clear from the figure. But the superposition principle total force due to the charge distribution is obtained by the summing over the forces to different volume elements. Here are the some formulas and examples which you can solve. These are the numericals which needs to be solved. It gives an overview. When a charged rod is brought near the neutral space, the sphere gets oppositely charged by the induction. Therefore, the sphere and the rod will attract each other. However, force of the repulsion between the two is not possible. Neutral metal objects, especially in industry, are often coated with electrically charged paint or powder particles. How do particles stick on the metal objects? The electrically charged paint or powder particles charge the neutral metal surface oppositely by the process of polarization. The particles stick on the metal objects on account of force of attraction between unlike charges. Figure this shows the two protons and one electron on the straight line BB. What is the direction of net electrostatic force in the central proton? In figure, the central proton is repelled by other proton along BA and it is attracted by electron again along BA. Therefore, net electrostatic force on central proton is along BA. Give some point to dissimilarity and similarity between electrostatic forces and gravitational forces. Dissimilarity. Electrostatic forces are between two charges and gravitational forces are between two masses. Electrostatic forces may be attractive or repulsive, but gravitational forces are always attractive. The electrostatic force between two protons is 10 to the power minus 10 to the power 36 times stronger than the gravitational force between them. Electrostatic forces operate over distances which are not large. Gravitational forces operate over very large distance. The electrostatic force depends on the medium between two charges. The gravitational forces does not depend upon the medium between two masses. Similarity. Both the forces obey inverse square law. Both the forces are proportional to the product of charges of interacting particles. Both are central forces. Both are conservative forces. If two objects repel one another, both carry either positive charge or negative charge. How would you determine whether these charges are positive or negative? To determine the polarity of the charge on the two objects, we bring one of the objects near to the positively charged glass rod. If the object is repelled away from the rod, it must be positively charged, as like charges repel. However, if the object is attracted towards the glass rod, it must be negatively charged, as unlike charges attract. What is the cause of charging? The cause of charging is the actual transfer of electrons from one body to another. An isolated conducting sphere is given a positively charged. Positively charged. Does it mean increase or decrease at the same? Its mass decreases slightly and loses some electrons. An ebonite rod is rubbed with fur or wool. What type of charges do they acquire? The ebonite rod acquires negative charge and the fur or wool acquires an equal positive charge. What is meant by quantization of charge? Charge on any body or particle can be integral material of charge on electron, which is given by Q is equal to NE. Why does the ebonite rod gets negatively charged on rubbing with fur? This is because the electrons in fur are less tightly bonded than electrons in ebonite rod. A glass rod rubbed with silk acquires a charge of 1.6 into 10 power minus 12. What is the charge on this silk? Charge on the silk is equal to and opposite to the charge of the glass rod, which is minus 1.6 into 10 power minus 12 coulomb. Name any two basic properties of electric charge. Quantization of charge, observation of charge. What are the value charge of an electron? It is the charge less and the value possible. Minus 1.6 into 10 power minus 19 coulomb. No charge less than this value does not exist. Does motion of a body affect the charge? No, the charge on the body does not change with motion of the body. Give 2 points of distinction between charges and mass. Charge can be positive, negative, or zero, but mass can be always positive. For the electric charge is always conserved, but the mass is not conserved as it is changed into energy and vice versa. What is the basic cause of quantization of charge? Only integer numbers of electrons can be transferred from one body to the another. Can ever photons have a charge? No, photons can never have a charge. This is because the charge cannot exist without rest mass. What is the following quantity depends on the state of rest or motion of a body? A. Mass, B. Length, C. Time, D. Charge, and E. Charge density and F. Phase. Mass, length, time, and charge density depends on the state of the rest or the motion of the body. However, charge, phase are invariant. Does Coulomb law of electric force obeys Newton's third law of motion? Yes, it obeys forces exerted by two charges on each other and always equal and opposite. Is an electric field force between two electrons greater than the gravitational force between them? If so, by what factor? Yes, electric force between two electrons is greater than gravitational force, but by them a factor of 10 to the power 42. Electrostatic forces are the much stronger than electrostatic forces on the given one example. A charged glass rod can lift a piece of paper against a gravitational pull of earth of this piece. Dimensional formula of epsilon naught is m inverse L minus 3 T minus 4A2. What is the prevalence of large value of K, which is 81 for water? It makes water a great solvent. This is because binding force or attraction between oppositively charged ions of the substance in water becomes 1 by 81 of the force between those ions in air. Forces of attraction between 2-point charges placed at distance d is F. What distance apart should they be kept in the same medium so that the force between them is F by 3? As F is directly proportional to 1 by r squared, new distance is equal to root 3r. In Coulomb's law, on what factor does the value of electrostatic force constant K depend? The value of K depends on the nature of the medium separating the charges on the system of the units. Superposition principle. Consider three charged particles P, Q, and R. If P, Q repel each other and P attracts R, what is the nature of the force between Q and R? Attractive, because Q and R will carry opposite charges. Does the Coulomb force with one charge exerts on another change if one charges are brought nearby? No, the Coulomb force does not force due to one charge on another change is not change. Coulomb's law. Dielectric constant of a medium is a unity. What is permittivity? As we all know, two small balls having equal opposite charge q coulomb are suspended by two particularly equal length meter from a hook fixed to a stand. The whole setup is taken in this satellite where there is no gravity. There is an angle between two strings in the tension each other's. In satellite there is a condition of weightless. Therefore, mg is equal to 0. On account of electrostatic force, the repulsion between the balls and the strings would become horizontal. Therefore, angle between the string is equal to 180 degree. What is superposition principle? After that, we'll answer these types. So these are some questions which need to be done. These are the numericals. Concept of electric field. When an electric charge Q0 is held in the victims or another charge Q, experiences a force of attraction or repulsion. We say that the force is due to interaction of electric fields of two charges, Q and Q0. Thus, electric field of charge Q may be convenienced as a space property by virtue of which the presence of charge Q modifies the space around Q, leading to the development of force or any charge Q0 held in the space. We may define electric field due to a given charge as a field that permeates the space around the charge, in which electrostatic force of attraction or repulsion due to the charge can be experienced by any other charge. If a test charge experiences no force at a point, the electric field at that point due to some other charge somewhere must be zero. The concept of the field was introduced first of all by Faraday. The charge Q which is producing electric field is called source charge, and the charge Q0 will test the effect of the source charge is called test charge. The source charge can be single charge or a group of discrete charges or any continuous distribution of charge. The electric field intensity at any point is the strength of electric field at that point. It is defined as the force experienced by a unit positive charge placed at that point. The electric field intensity at this point is given by this particular formula. The SI unit of the electric field intensity is Newton per Coulomb. Electric field intensity is obviously a vector. The direction of E electric field is the same as the direction of force. Electric field is along the direction to which the test charge plus Q0 would tend to move it free to do so. For a positive charge, source charge, the electric field will be directly radiated outwards from the charge. If the source charge is negative, the electric field vector at each point is radially inwards. As the test plus Q may not be its own electric field, it can modify the electric field at the source charge. Therefore, to minimize this effect and ultimately remove it, we rewrite the electric field intensity at R by this formula. As the magnitude of test charge Q0 decreases, the electric field intensity at the point defined more and more accurately. On account of discrete nature, the charge of the minimum possible value of test charge Q0 is 1.7 10 per minus 19 Coulomb, which is a unit charge. It cannot be a zero. However, on the microscopic scale, it is good as taking as a limit Q0 to 0 if the small test charge Q0 positively and measured value of electric intensity will be somewhat less than the actual value of the electrons intensity. However, if the small test charge Q0 is negative, the measured value of electric intensity will be somewhat more than the actual value of the electric density. What is the role of electrostatic play in reproduction of flowers? Two important parts of the flowers are flower anther and flower stigma. The formers of electrical insulated at the later of the electrical connected to the ground through flowers interior. The bees are usually positively charged and the pollen grains are moderately conducting. When a bee hovers near a flower anther, pollen grains being so light jump on the bees on account of electrostatic force of attraction. The grains cling to the bee during the flight and to the next flower. As the bee comes closer to that flower stigma, the pollen grains jump from bee to the stigma in direction of the electric field between the bee and the stigma, resulting in fertilization of the flower. What is shark pod? A shark pod is a protective ocean device which has been developed to protect divers from sharks. Sharks are known to be sensitive and weak electric fields. A shark pod consists of two metal electrodes, one attached to the diver's fin and other to the diver's air tank. These electrodes produce a strong electric field around the diver. The charge, being sensitive even to weak electric waves, is turned away to the distance up to 7 meters from the diver. Electric field intensity due to a point charge. Suppose we have to calculate electric field intensity at any point P due to a point charge Q and 0, where OP is equal to R naught. Negative is a small point test charge Q naught at P. Then the R value of vector is towards Z. Electric field intensity at any point is due to the group of point charges, which is equal to the vector sum of the electric field intensities due to the individual charges at the same point. For this, we calculate the electric field intensity at the given point P due to individual charges, as if other charges were not there, then they were theorem. Then theoretically, this is a formula. Now suppose the point charges Q1, Q2, Q3, Qn are located in the vacuum at the position of vector R1, R2, R3, Rn respectively. We have to calculate the electric field intensity at the point P, whose position vector is R0, as the net force of the P is vector sum of the forces due to individual charges. Therefore, we can write. Note that the electricity is a vector quantity, varies from one point to another point in the space. Its value depends on the position of the source charges. The direction of electric field due to the group of discrete charges is determined using the polygon law of vectors. Electrical field intensity due to continuous charge distribution. In the previous chapter, we have studied 3 kinds of continuous charge distributions in an article. As explained already, total force on small test charge due to the linear charge distribution of density is particularly this. Electric field intensity at location R0 due to linear charge distribution is given by this formula. Similarly, we have 2 more formulas which you can go through. Electrical field lines. Electrical field lines map pictorially the electric field around the configuration of electric charges. The concept was developed by Faraday and is a non-mathematical way of visualizing electrical fields around the charge configuration. We may define an electric field line as a path straight or curved in an electric field, such as tangent to it at any point gives the direction of electrical field intensity at that point. In fact, in this path, along with the unit positive charge actually moves in an electrostatic field. If free to do so, AB is the electrostatic line of force. The tangent to the line at any point P gives us the direction of electric intensity EP at P. Electric field at P is given at P. Similarly, tangent AB at the Q gives us the direction of EQ. The field outwards the line of the force extended to the infinity. On the contrary, the lines of the force due to a single negative point charge are directly inwards. Show lines of the force due to the pair of equal and opposite charges forming an electrical dipole. They show clearly the mutual attraction between the opposite charges, as it is clear from the field lines due to 2 charges Q1 and Q2 exert lateral pressure on each other, which is responsible for repulsion between like charges, and further in the point P, repulsions at the neutral point where the net electric field intensity is said to be 0. These are the particular images which is needed to get clarified and which is needed to do a clarification on this particular concept. Here, the figure 1.7, it shows the direction of electron at electric field at P and electric field at Q, which is getting towards the tangent. Positive field charge, positive test charge, which is repulsing away from that, and the force of direction of force is at right side. In this particular diagram, positive test charge, The positive charge is inwards, as the force must be gained to the left side. In this figure, it shows like a magnet. For details, you need to study this particular image. And this particular image of is the particularly diagram of positive test charge. And this is a positive test charge which is outwards, and this one is of inwards.